All right, in this video, we are going to look at functions. We're going to try to do a fairly basic introduction to the idea of functions and some of the things we want to do with them. In particular, we're going to talk about what functions are, how different ways we can represent them, and then in the second part, we're going to look at some specific types of functions and problems that we might see with them, focusing on linear functions, but looking at some other ones as well. So at its most basic, a function is just a relationship between two groups of objects. And most of the time, those are going to be numbers with the functions we're looking at, but they don't have to be. And in general, a function takes an input and gives a unique output for each of those inputs. We call the collection of allowable inputs the domain, and the collection of allowable outputs the range of the function. So we have a domain for inputs and a range for outputs. And the first way that we can represent functions, and often how we start, especially in a context situation, is trying to describe a function just in words. So we might say something like, there is a function that gives the height of a plant after a certain number of days since it was planted. And then, for units, we might measure the height in centimeters. Think of that as the output, and the number of days is the input. Another function we could describe would be the relationship between the length of a side of a square and its area. So we could consider the length of a side as the input, and then the area as the output. So there's a function relationship there. And then another example might be the function that relates the temperature to the time of day. So we can think of the time of day as the input, and then the temperature, maybe in degrees Fahrenheit, as the output. But once we get started with words, usually what we want to do is try to visualize functions. And so the next thing we're going to look at is how to represent them in tables and graphs. So what we're going to do is we're going to head on to Desmos real quick, and we'll take a look at ways we can represent functions. So the first way is as a table. So you can see here we have two columns. We have the left-hand column that has an x sub 1 at the top, and those are usually where we put the inputs for the function. And then in the right-hand column, in this case labeled y sub 1, we put the associated outputs. So each input is associated with exactly one output, and they make an input-output pair for the function. And so you can see here that for the first 4 days, the plant did not grow above ground, at least. So it had a height of 0 centimeters during that time. But then on the 5th day, it grew to have a height of 0.5 centimeter. And on the 6th day, it was 1.5 centimeters. And the 7th day, it was 3, and so on. And so in this way, we can represent this relationship between the number of days since the plant was planted to the height of the plant. All right, so a table can be nice, but it is often very useful to have a visual representation of the function. One of the things that's really nice about this is it's pretty easy to see. There are some kinds of relationships that are just easier to see in a graph. For example, it's very easy to see in the graph that over time the plant was getting taller if we represent the height. An important point to note is that each of these points corresponds to an input-output pair. We usually put the inputs on the x-axis and the outputs on the y-axis. And so 3, 0, right on day 3, the height was 0 centimeters, and that is right here. This is the point 3, 0. And then down here we have the point 7, 3, so that means after 7 days, the plant had a height of 3 centimeters. And I've used dots to represent this because the data that we have from the measurements is only these points, so technically that's the function. The function is can be represented by those dots. Now, of course, the plant was growing in between those times, and so it might be useful to connect those dots. And so certainly the plant was in between those points as it grew. Now, it might be nice sometimes in certain situations to want to have an even more smooth model of what was happening. And you can see this purple graph doesn't exactly hit all the dots, but it's a nice smooth kind of representation of that shape. And that can be useful too. We're not going to be too worried about how to describe that function. I just wanted to show you one of the ways that we can look at models for functions. All right, so we have a table and a graph that kind of go together to help us visualize a relationship that the function represents. So let's head back over to the slides and look at another type of function. So let's look specifically at the example I talked about where we have the length of a side and its relationship to the area. So if we draw a square that is 1 centimeter on a side, we can make a table of those values. And when the side is 1 centimeter, the area is also 1. In this case, centimeters squared. If we draw a bigger rectangle that is a square that has 2 centimeter side lengths, then its area will be 4 square centimeters. And so we are building this table that represents this function relationship. We could keep going. It's pretty easy to calculate the area given the side length of a square. So we could have something like 3, side length of 3 corresponds with an area of 9 square centimeters. Another way that we could represent this function is also with a graph. And so again, we put what we think of as the inputs or the independent variable on the horizontal axis. I'm going to call that S in this case. And then on the vertical axis, we put the outputs, or what we think of as the independent variable. So in some sense, you can think of the area. Did I say that backwards again? The outputs are the dependent variable because in some sense they depend on what the inputs are. So we could plot these points. So I used a kind of a brownish pink color to represent the point 1, 1. And then green is going to represent the point 2, 4. That's an input-output pair that we have for this function. And then finally the point 3, 9. And again, these are not the only points that we could have for the area of a square given a side length. So we could connect those with a nice smooth curve, recognizing that anywhere along there, that same relationship is going to hold between the side lengths and the area. And that is exactly what a function is. It's describing a relationship between two groups of objects. And in this case, and oftentimes, we're going to look at numbers. So one last thing we want to do with graphs in this segment is to see what information we can get from the graph of a relationship, the graph of a function. So again, we'll hop back over to Desmos, really wonderful tool. And here, this green curve represents the graph of a profit function. So the horizontal axis, or the independent variable, is standing for the price of juice. And then the vertical axis, or the dependent variable, is representing the profit for this company in millions of dollars. So depending on how much they charge for their juice, they can project how much money they expect to make based on data that they've collected, I imagine. And so, there are some questions we could ask ourselves, and perhaps the graph can help us. One thing that's important to be able to do is to understand how to find data in the graph itself. So for example, if the company charged $2 for their juice, approximately what would be their profit in terms of millions of dollars? So I invite you to pause and look at the graph and try to answer that. And hopefully what you find is that if you go to the input of 2, and then you go up to the curve, it's right around $27 million. So the input-output pair 2 and 27.41 million is the input-output pair for that. And so that tells us the profit at that particular price point. Another thing we could do is we could ask ourselves, at what price point would we get the maximum profit? So I invite you to, again, pause and look at the graph and see if you can identify that. And so again, if we follow this input, what we're looking for is the maximum profit, which looks like this peak up top. And so that looks like it's somewhere around, what is that, 1.4, 1.3 something. Looks like it says 1.317. So somewhere around $1.30, according to this projection, is the price that they would want to use if they want to maximize their profit. What else can we figure out? Well, let's try to understand what this graph is telling us about how price and profit are related. So one thing you might notice is that when we have a 0 output here, what does that mean? The price is 25 cents, but the profit is 0. Well, one thing that could mean is that that's something like a break-even point. So when we only charge 25 cents, we actually don't make any profit, which means the money that we come in only is enough to pay for the cost of everything we were doing. And similarly, well, let's follow this now. What happens? As we increase the price, the profit is also increasing. Until, it's increasing until we get to that $1.30, $1.32 if we round. That seems to be about the maximum price we can charge. And after that, our profits don't go up anymore. Now it seems like maybe our prices are too high and people are not interested in the juice. And so our profits actually begin to go down until, again, we get to $2.50. And now, again, the demand is so low that we're just barely covering our costs and we're actually making 0 profit at that point. So those are some of the things that we can get from the graph of a function. And you'll have the opportunity to practice kind of interpreting graphs in that way yourself. In the next segment of the video, we're going to look at the fourth and final way that we represent graphs, which is in terms of equations. All right, so now we're going to look at how we can represent functions using equations. And really, this is one of the more useful ways that we can do, especially when we want to do some calculations and some algebra. It's nice to have an actual equation to work with. So as a simple example, we had our area function earlier, where if we know the length of the side of a square, we can calculate the area. And here's an algebra equation that gives us that. So we can think of, again, the input as the side length. We think of as the independent variable. And then the output is the area, which we think of as the dependent variable, because the area depends on the side length in some sense. Now, oftentimes you'll see, especially in textbooks, so when you're teaching children, this is what you'll come across at this point, is the input variable is usually called x and the output variable is called y. It isn't necessary to do that. As you can see, when we're talking about area and side length, it seems really natural to use a and s, but oftentimes we use y and x for functions, especially when there isn't a context associated with them. So for example, we could have a function like y equals negative 2x plus 1, negative 2 times x plus 1. So let's think about what we could do with this. One of the things we could ask is, what happens when we input 3 into this function? So I'd invite you to pause the video, take a minute, and give that a try. So what we're going to do is we're going to replace x, or substitute, with the value of 3. So we want to know what's the output when we do that, or what value does y have? So if we plug in 3, we get negative 2 times 3, which gives us negative 6. And then we add 1 to that, and we come out with negative 5. And so what that means is the point 3, negative 5 lies on the graph of this function, or another way to think about it is that 3 and negative 5 are an input-output pair. So another thing we could ask with the same function is there an input that gives the output of negative 13? So I'd invite you to, again, pause the video and give that a try. So what that means now is we're going to use negative 13 as the output and try to figure out what x would do that. And one way to do that is to use our algebra skills to isolate the x variable. And hopefully we have an equation then where we can see visually what x should be to make the statement true, to make the equation true. So one way we can go about solving this in terms of, remember, balancing, as we saw in some of our previous videos with algebra, we can subtract 1 from both sides, take 1 away. So then we're left with negative 14 should be equal to negative 2 times x. And at this point, we can probably reason our way to what value of x would make this true. But we can also follow the rules of algebra and try to isolate the x. So we could divide both sides by negative 2, break both sides up into 2 equal groups, and then each group would be x and 7. So x should be 7 to make this true. And again, what does that mean? That means the input 7 corresponds to the output of negative 13. 7, negative 13 lies on the graph of this function. All right, so those are the ways that we can represent functions as words, tables, graphs, and equations, and all of them are useful in different situations. What we're going to look at in the next segment is specifically types of functions, beginning with linear functions. All right, so a linear function is called that because its graph is a line. Now, more complicated situations have interesting features, but for our purposes, we can focus on this. The graph is a line. And now let's go again over to Desmos. The equation that you'll often see associated with a line is y equals m times x plus b. And we'll unpack what those values are and what they mean, again, by looking at a little interactive Desmos graph. So here I have input y equals mx plus b, and it has graphed this blue line. And you can see I've got these nice sliders here for what values m and b have. So we think of, again, x is the input, y is the output, and m and b stand for specific numbers that we might have in a situation. And so what do these values do? Well, you can see that the b value, as we increase it, the line slides up, and as we decrease it, the line slides down. And more than that, when b is 1, you'll notice that the graph touches the vertical axis at 1. And when b is 5, we touch the vertical axis at 5. So b is often called the y-intercept for that reason. So when it makes sense in the domain of the function, we call b the y-intercept because it's where the graph touches the y-axis. So let's go back to 0 for now. And now what happens when we change this m value? This m value, in some way, is a measure of the steepness of a line. And specifically what it tells us is it tells us the ratio between the change in y and the change in x, or the change in the outputs with the change in the inputs. And one thing that's true of a linear function is that that ratio is constant. So anytime you change the outputs and there is a corresponding change in the outputs that gives a constant ratio. We often call that slope, and we measure it by thinking of the rise, the change in y, the rise, over the run, which is the change in x. And so we can visualize that. So you can see these green bars represent a change of 1 in x, or the inputs, and then the red bar tells us the corresponding change in the outputs. And so right now, the slope is 2, when what that means is the y will change 2 for every 1 that the x changes. Positive 1 gives a change of positive 2. And if we increase that to, say, 4, now you can see every time we go over 1, the graph goes up 4. And it does that consistently everywhere. That ratio is always the same. And if we make the slope negative, what that means is when we go over 1, we actually go down, in this case 2, when the slope is negative 2. Over 1, down 2, over 1, down 2. And so a line has a constant slope, or that ratio is always the same between the change in y and the change in x. Okay. So the next thing that we want to look at is an example. So let's look at an example that we can model with a linear function. So let's say at the cafeteria, you can get a lunch special that includes a drink and a salad. The drink costs 85 cents, and the salad costs 35 cents per ounce. So what we'd like to do is express the total cost of a lunch special as a function of the amount of salad. So before we try to do this general function, let's just think about a specific example. Let's calculate how much it would cost if we had a 20-ounce salad. Now, a 20-ounce salad is enormous, right? 16 ounces makes a pound, so we have more than a pound of salad. But let's just figure out how much that would have cost in this somewhat extreme example. So we know the soda, why is it a soda? The drink that comes with our lunch will cost 85 cents. And then we know that each ounce of salad costs 35 cents, so we'd have to multiply the number of ounces times 30.35 to figure out how much we would have to pay. And of course, we could use a calculator to do this, but it's nice when it's possible to kind of flex our mental math muscles to strengthen those and improve our numerical reasoning. So I noticed that I can break 20 up into 2 times 10, and that's a little easier to deal with because I can find 2 times 0.35 is 0.7, right? 35 times 2 is 70. And then all I have to do is then multiply by 10 to figure out the number of dollars. And so I get $7, and then the drink was 85 cents, so the total becomes $7.85. So now what we want to do is generalize that process. How can we think of that as a function? Well, we can think of the output as the total cost of the lunch special. We'll call that y. And then we can think of the input as the ounces of salad that we get, which we'll call x. And if we do that, then we know we can calculate the total by taking the amount of a drink, which was 0.85 of a dollar, right? 85 cents. And then we multiply the number of salad ounces by 0.35. And that function, that equation, will give us the total for any salad amount that we want. And so that is a way to represent this relationship between the ounces of salad and the cost with a function. Another example we could look at is a delicious Arnold Palmer drink is a mixture consisting of 1 part lemonade and 2 parts tea. This might sound a little bit familiar to some of you. So what we want to do is try to express this relationship of lemonade to tea as a linear function. So a way we might do that is to start making a table. We know that 1 part lemonade goes with 2 parts of tea. So if we double that recipe, we know that we should have 2 parts corresponding with 4. And we don't have to go one at a time. We could think about if we wanted to have 8 parts lemonade, well, we know we'd have to have twice as much tea to keep that mixture in a constant ratio. And so we could think of the outputs. Now, this one is a little bit different because which one is independent and which one is dependent is not really very clear. So we can really choose whatever we want. I'm going to look at y as the output in terms of the parts of tea. But you could just as easily flip this around. The equation would be different, but the function would be the same. Right? It's the same relationship between these two quantities. So I'm going to call y the parts of tea and x the parts of lemonade. And if we do that, we know that whatever the lemonade is, we're going to multiply that by 2 to get the parts of tea that we need. Okay. All right. Next, we're going to look at an example of tables to try and identify if there's a linear relationship present. All right, before we move on to examining some tables, I just wanted to draw your attention to the idea that this linear function is having a constant ratio between the change in y and the change in x actually has some nice connections to the way we've been talking about mixtures and ratios in terms of multiple batches. So I'd invite you to think for yourself how that connection could be made here. One of the things that we might want to do is try to identify in a table whether or not the function represented is linear. And so I'd invite you to think about how could we do that? What are some ways that we could do that? Well, one of the ways we could do that is we could certainly plot these and see if the points form a straight line when we connected them. But another way that's useful to think about is to analyze the change in y over the change in x. So if we look at this first table, what you'll notice is that the y values are going up by 4, but then they go up by 8 and then by 16, while the x values are going up by only 1 each time. And so the difference between these values is actually getting bigger each time, while the difference in the inputs is staying the same. So the ratio of the change is actually getting bigger. Right? The first ratio is 4 to 1, but the second ratio is 8 to 1, right? Because that change in x is 1 each time. So this one is not linear. The middle function, we can see the change in y is -2 each time, and the change in x is 1 each time. And so that does represent a constant ratio. So this one could represent a linear function with the data we have here. And finally, we have the last 2 columns, which are the change in y here is 6, and the change in x is 6. Now the next change in x is only 4, but you'll notice that the change in y is also 4. And now the change in y is only 2, change in x is only 2, but the change in y is also 2. And so each of these cases, the ratio of the change in y to the change in x is actually 1. And so this one also could represent a linear function. So let's take a minute and think about what are some examples that we could have that are nonlinear. So let's say that we bought a car for $4,000, and now unfortunately it loses 20% of its value every year. So one thing we could ask is, well, how much is a car going to be worth after 5 years? So the first year, before we jump to 5 years, let's just try to think about what would happen after a year and then maybe 2 years and see if we can see a pattern. So what we can see here is if we take the original value, it loses 20%, so you can think of that as keeping 80% of its value. 80% of 4,000 using a calculator gives us $3,200. So after 1 year, the car is worth $3,200. Now, when we want to calculate the depreciation or the change in value for the next year, we don't start with 4,000 again, right? The car isn't worth that much anymore. So now it's only worth 3,200, and it's only going to keep 80% of that value. But what I'm going to do is I'm going to represent the value at the beginning of the year with $4,000 times 0.8 or 80%, and then we're going to multiply that by 0.8 again, find 80% of that value. And the reason I want to do that is because I can see that if it's losing value every year, or it's only keeping 80% of its value every year, then every year we're going to multiply by another 0.8. And that repeated multiplication we can represent as an exponent. And so if we want to capture the loss in value after 5 years, or what the value will be after 5 years, we can take 4,000, the original value, and then each year we're going to multiply by 80% or 0.8. And we're going to do that 5 times. So we're going to take 4,000 times 0.8 to the 5th. And that gives us the value of $1,310.72 after 5 years. And in general, we could represent this relationship between the number of years since we bought the car and the value of the car, V for value, right, as an exponential equation. This is definitely not linear because we're multiplying by 0.8 each year. So functions that grow or decay with repeated multiplication are called exponential functions. And with these functions, one of the key features is that you're going to see the input variable in an exponent somewhere. So some simple examples that look like exponential functions here. You can see that x is up in an exponent. Another type of function that you're probably familiar with is a quadratic function, which we call it quadratic because the highest exponent is 2 in the equation. And 2 is often called squared. Right? When we raise something to the second power, we say that it is squared. And quad is supposed to remind us of a square. So that's why functions that have a highest exponent of 2 are called quadratic equations. And I'm sure you've seen these many times. I wanted to show some examples that maybe don't look like they have an exponent of 2, but if you multiplied them out, you would see that the highest exponent that shows up is 2. So these are some of the kinds of functions that we're going to look at and become a little bit more familiar with, but that is our introduction to functions.